Okay, so let's do a quick example for energy conservation that involves angular quantities. So what we're going to do here is we're going to revisit a pulley and block problem, but in this case the pulley has mass, so it's not an ideal massless pulley like we're used to dealing with. So as the pulley starts to rotate, um, it will gain rotational kinetic energy. And that's going to have an effect on the velocity that the block hits the ground at. Here we've got a really quick sketch of bar graphs of the energy. So the total mechanical energy in this situation is conserved since the only force acting on the system, uh, where we define the system as the block and the pulley, is gravity, which is a conservative force. Initially, we start with some amount of potential energy. We're not going to worry about the potential energy of the pulley because it's not going to move up or down. So the change in the pulley's gravitational potential energy will be zero. The only potential energy we care about is the block since it's going to be moving up and down. Um, Once the block starts moving, the pulley will rotate as well, and that's going to give them both a shared kinetic energy. Notice that this problem is different than the Atwood's machine where we used to have a block hanging off to the other side. Um, for an ideal pulley where there's no mass, a block connected to the pulley with nothing else resisting the rotation um, would just fall with an acceleration of 9.8. However, in this case, the block will fall down more slowly than free fall because the pulley having mass is going to have an inertia that's going to take some effort to get rotating. So let's see how we can put that information into some math. Because we said before the only force acting on the system is conservative, we know that the energy is conserved. And initially, the only energy we have is gravitational potential energy. So we've got mass times gravity times height. We could also put in the gravitational potential energy of the pulley, but we're not going to with the understanding that the pulley never changes height. So we would have the same terms showing up on both sides of the equal sign. Um, all we really care about is the change in gravitational potential energy. So since it's not changing its gravitational potential energy, we're just going to ignore it. So the block has gravitational potential energy of mass times gravity times height. And the final um, energy is all kinetic. Since the block is just about to hit the ground, the block's going to have 1/2 mass times its velocity squared. But the pulley, because it has mass, is also going to have energy related to its rotation, and that's going to be 1/2 the moment of inertia times its angular velocity squared. And there's a couple of things that we can use to simplify this equation further. One, we can say if if the string unwinds without slipping so that there is a direct relationship between the translational speed of the block and the angular velocity of the pulley, then we know that the angular velocity is equal to the speed of the block divided by the radius of the pulley, r. Um, we also know that the moment of inertia of a cylinder is, and this is a solid cylinder, so that's going to be 1/2 the mass times the radius squared. So putting that all together, we're going to get that this term, well, mass times gravity times height, equals 1/2 mass velocity squared plus 1/2, and then we're going to have 1/2 mass r squared times v over r squared. So these two r's are going to cancel out since they're both squared, and we're going to end up getting mass times gravity times height equals 1/2 mass velocity squared plus 1/4 mass of the pulley velocity squared. And we can put that together. Let's multiply both sides by 2. So we're going to get 2 mgh equals m plus m over 2 times velocity squared. I'm just doing a little bit of rearranging there so that it looks a little bit nicer. And then let's try to solve for the velocity of the block before it hits the ground. So we're going to have 2 mgh over m plus m over 2 equals the velocity squared. We could try to simplify this a little bit further as well. We could divide the top and the bottom by m, just so that the mass doesn't show up twice in the equation. And so if we did that, we'd get 2gh over 1 plus m over 2m, and then we could take the square root of that. And so that would be the equation for the velocity of the block just before it hits the ground. And you can see if the mass of the pulley was 0, this equation would simplify. So if the mass of the pulley is 0, meaning that it's an ideal pulley and it didn't really have a moment of inertia, the equation simplifies to 2gh over 1, which is just root 2gh, and that's the equation that we derived previously when we did objects in free fall falling a distance h. So it's nice to check in that way to make sure that the equation reduces to a simpler case, and it does. So